In this lecture, we will see in detail the time-dependent perturbation theory. First, we will take the unperturbed time-dependent wave vector get psi sub n, which is equal to e power minus I e n t over h cross multiplied by this get u n. Here, the time-dependent factor comes in the exponential term. This un is time independent. That is, it depends only on spatial coordinate. So we have adopted the variable separable technique. Now what we are going to do is the get psi can be written as on the basis of psi sub n. So for that I am multiplying this by 1. Uh, that is get psi. I am multiplying this get psi by 1 using the completeness property. Summation over n, the outer product of psi n with psi n is equal to 1. We know very well. Now you take this brass iron and get psi, brass iron and get psi. This is after all a number because it's a scalar product. This will give you a number, of course, which depends on time. So this expansion coefficient, which is designated as an of t. So this summation can be written as summation over n, an of t get psi n. Here you have get psi n. Hence, the above equation become psi. That is, psi is equal to an t. This get psi n. We have taken get psi n as exponential e power minus I e n t over h cross multiplied by the get un. So we got this total wave function in terms of the wave function psi n. That is, we have changed the spaces, and psi n also we have separated into two parts. That is time dependent part and spatial dependent part. Now take the Schrodinger equation IH cross delta psi over delta t, which is equal to h psi. You just take the right hand side. This Hamiltonian can be separated into two parts. One is unperturbed Hamiltonian H naught, we know, plus the perturbed Hamiltonian. Naturally, this depends on time. H prime, which is a function of theta, multiplied, which is multiplied by the lambda parameter. I have already explained about this lambda parameter. Of course, is multiplied by this wave function. Just now we have seen that psi on psi can be written on psi n basis as summation over n an of t e power minus I e n t over h cross get u n. Substitute this in the above equation. Now you take the left hand side. So IH cross I have taken outside this summation because it's a constant. So summation over, you keep an of t as it is, then you differentiate only the exponential term, which will be minus I en over h cross power minus I en t over h cross un. Then next term, you keep the exponential term as it is, you differentiate this an. So this will become an dot. That is a time derivative of an. So similarly, the right hand side, here you have h naught times psi. So psi, the summation term, and h naught is an operator which will operate on un. Then next second term is lambda times lambda. I have mentioned here, and h prime lambda h prime. Remaining things are psi. So second term will be an of t psi x, then this exponential term h prime un. Now you come to the left hand side. See, you have I h cross here and I h cross here, and here minus I over h cross. If you multiply both, h cross will get cancelled. Here you have I, and here uh, minus I. So I into minus I, you will get plus 1. So this will become 1. So this is simply you will get an of t en exponential term, then it is un. Now you come to the right hand side. Here, if h naught act on un, you will get the energy eigenvalue en. Now you compare the first term of right hand side and first term of left hand side. So if you compare this left hand side and right hand side first term, both are exactly identical. So both will get cancelled each other. Now you have only the second term. Second term of the left hand side and second term of the right hand side. So we have taken the second term of the left hand side and the second term of the right hand side. And now you take a inner product with the UK. Use Dirac notation. Un can be written simply as get n by Dirac notation. We are going to take inner product with UK, that is k, uh, inner product of k with n. Then you come to the right hand side. Here, except k and n, all other things are constant. So I have taken it out. Here it is not like that. H prime is an operator, so you cannot take it out. So here, when if you take inner product, it will become k h prime n. Now, first we will solve this summation over n kn. So this will be only if n is equal to k. Otherwise, all other term will become zero. Naturally, the summation will go away. You will get I h cross, since n is equal to k, I have written a dot ak dot, which is a function of time t, and en will become ek. Then right hand side I will keep as it is. Now you can see this exponential term. Exponential term, you bring this to the right hand side. This minus will become plus. Here you remember that this is ek, this is en. So this will become ek minus en t over h cross. Of course, it is lambda. All other thing I kept constant, kept as it is. So, and you also bring I h cross to the right hand side. This will become I h cross inverse. So, in the left hand side, you have only ak dot, which is a function of t. Right hand side, you have this term. Now we will see further what will happen to this. Now we got this expression a k dot t, which is a function of t, is equal to I h cross inverse summation over n a n of t e power I e k minus e n t over h cross lambda times this inner product k h prime n. Uh, Here, ek minus en divided by h cross can be written as omega kn. So this will become this exponential term e power I omega kn t, because e k minus en over h cross is omega kn. So this will become omega kn t e power I omega kn t lambda k h prime n. This equation where the important point is omega kn is equal to ek minus en over h cross, as I have told you just now. This is called four angular frequency. This omega kn is 4 angular frequency. Uh, so energy is a H cross omega. So H cross will get cancelled. You will get omega kn. So this is the 4 angular frequency. This equation is the fundamental result of time-dependent perturbation theory. This is the fundamental result of time-dependent perturbation theory. So we have seen the time derivative of the expansion coefficient ak dot, of course, which is a function of time. So for simplicity, I have just mentioned ak dot 1t, which is equal to I h cross inverse summation over n a n of t e power I omega k n t lambda k h prime n. So here I am going to express A as power series in lambda, as what we have done in the case of time independent perturbation theory. An can be written as an0 lambda an1 lambda squared an2, and it will go like this. Uh, as we are interested only first two terms, I have taken up to the second order. Up to the second order correction. Then similarly, ak dot is equal to ak dot 0 plus lambda ak dot 1 plus lambda squared ak dot 2, and it will go on. So now substitute this in this equation, above equation. So the a dot k, this green color bond, I have taken in the left hand side, and an, uh, which is given in red color band, I have taken in the right hand side. So I got this expression. Here you can notice that there is one lambda factor here. You bring this lambda inside the bracket. So this first term will become lambda times an0. The second term will become lambda squared times an1, and lambda cube. It will go on like this. So there is no change in the left hand side. We will see how we can reduce further. So we got this expression. Now you can equate equal power of lambda. First you take lambda power 0. There is no term with lambda power 0 in the right hand side. So ak dot 0 is equal to 0 because no terms without lambda. That means ak of 0 is a constant. Only when you differentiate the constant, you will get 0. That is one point. This is the first equation. Then next you can compare the lambda term. If you compare lambda term here, an0, ak dot 1 is equal to am0. Similarly, the lambda squared term, here you can see lambda squared term an1, that is ak dot 2 is equal to an1 here. So always this right hand side lags by 1. That is here uh, ak dot 1 is equal to here ak dot 0. Similarly, the ak dot 2 is equal to this an1. So 1 always less here. Here this is left hand side always advanced by 1. So this can be generally written as ak dot s plus 1, because this is always in advance, is equal to I h cross inverse summation over summation over n an s. Now you can understand yes, because this is always less than 1 less than this left hand side. So ak dot 1 means here you have ak dot an0. ak dot 2 means here an1. So it will go like this. So now if you take s equal to 0, then ak dot 1 will become uh, equal to minus IH cross, sorry, IH cross inverse summation over n, an 0 of t, because we have taken s as 0, e power I omega kn t k h prime n. This is what we got at, finally we got this. So we got this expression ak dot 1 is equal to IH cross inverse summation over n, an 0, which is a function of t, e power I omega kn t bra k h prime get n. This is the final expression we got. Here, see, n is an running index. So an 0 can be a1 0, a2 0, a3 0. It will go up to n. Assume that at time t equal to 0, that is just before applying the perturbation, that is we are in an initial state. Hence, all except one of the an 0 are 0. It is reasonable. This assumption is very reasonable, because at the initial state, you can have only one coefficient, because the system is initially in an definite unperturbed energy state. So, an of 0 is equal to get spra n inner product of n with m. This is so uh, this is equal to delta nm. That is, it is one only when m equal to n. Otherwise, it is 0. So now you take n value as m, n is equal to m, then it is 1. All other term it will be 0. So first to take the first term as m. So this will be am 0, and omega kn will become omega km, and also this get n will become get m, because we are assuming that am at the initial condition this n is equal to m, so am also equal to 1. So this only this term exists. All other term in summation will be 0. That is, when n is not equal to m, this summation will be 0. So you can neglect this summation. So you will get only the first term. Particularly here, we have taken am of 0 is approximately equal to 1. That is, maximum contribution is from only from this coefficient. So now we got this expression ak dot 1 is equal to IH cross inverse am 0 e power I omega kmt pra k h prime get m. So this is what we got now, and we assumed that and also, which is a reasonable assumption, that am 0 is 1. So this expression can be reduced to ak dot 1 is equal to IH cross inverse e power I omega kmt k h prime m. So now you take, I can explain this example using this simple diagram. See, this is the time. I am giving the perturbation when time t equal to 0, and I am keeping the perturbation up to the small interval tau. So then our ultimate aim is we have to find the expansion coefficient. That is, if you integrate this ak dot 1, then you will get ak 1. So your integration is between 0 to tau. So this will become IH cross inverse integral between 0 to tau e power minus, sorry, e power I kmt k h prime m, that is pra k h prime get m integrated over a time. This equation is used to compute the transition probability for a general time dependent perturbation. This is very, very important relation. We are going to use in all the case where we are going to find the transition probability for the time dependent perturbation. Thank you very much for watching my video and supporting me continuously.